Big Bang Theory. It's by far the most prominent model of the universe that's out there because it's still the most widely supported, and with generally good reason. The fact that it is so widely known, though, doesn't really dilute that at its heart, the Big Bang is still pretty darn cool. It argues that way back in time, around 13.8 billion years ago, the entire universe was held within an infinitely dense singularity. This was essentially a pretty mind-shattering moment, the very first moment of all moments, when everything there ever has been and will be was contained within one single point. From there, it expanded, and expanded, and expanded. Cosmic inflation meant that the universe grew vaster and vaster, but again, all that it has ever needed to grow was originally held within that initial singularity. As we know that inflation is accelerating too, we know that the Big Bang is by no means finished. It's ongoing, with the cosmos growing out and out, replacing the very literal nothingness that surrounds it with the ultimate somethingness of time and space. Again, and importantly, the Big Bang easily ranks as the most accepted theory to explain the universe. But still, it isn't complete, and it isn't uncontested. For one, what else do we know that has a singularity? Our second theory is known as black hole cosmology. As massive and ominous consumers of all things, black holes need little introduction. There are various types, largely ranked by their incredible masses, but in general they form whenever large enough stellar objects collapse. And alongside their somewhat merciless reputation, black holes serve as something like anchors within the universe, weighing the rest of space down around them. For example, most galaxies are thought to have at least one supermassive black hole at their center, around which everything else gravitates. One especially interesting region of a black hole, however, is the event horizon, the calculated barrier beyond which it is impossible to escape the black hole, and where the laws of physics break down. Black hole cosmologists, though, ask us to ponder that setup from the inside. Imagine that you were on the inside looking out. It could be, or perhaps would be, that same event horizon would mark the limit as to how far you could ever see or understand. Inside your black hole, there would be an observable and unobservable reality. But we already have that concept in the here and now. We know that the observable universe is some 93 billion light-years across, and beyond that, who knows what? The unobservable is, naturally, inevitably, unknown. Physically, mathematically, it's as though we are inside a black hole. It's the same overall structure, and black hole cosmologists suggest that it isn't only a coincidence, it's actually the truth. If we are all black hole babies, then there's another probability at play as well, that this universe isn't the only one that's out there, that there could potentially be other universes within the black hole inside this one, and that there could be other black holes beyond the one that we're in. Black hole cosmology certainly isn't alone in this kind of multi-layered approach. The brain world model is another that lends itself towards a more multiversal way of thinking. Advocates argue that this universe, our universe, exists something like a sheet of paper blowing around in the wind. There's randomness to the way it moves, apart from the fact that it's in some way contained within another, much larger structure. There are also other sheets of paper, though, i.e. other brains or membranes being tossed about in much the same way. The larger structure is then known as the bulk, and the theory itself is sometimes referred to as the incredible bulk theory. As to how the bulk itself was born, there is no universal consensus, even among staunch brain world supporters, although black holes have again been proposed by some as a potential way that separate brain universes could be linked. Tied together, but also impossible to detect for anything that's essentially trapped within one of those brains. Now, this particular universe perhaps isn't infinite, but we would never get to know that. So really, from our perspective, it might as well be endless. There are some slightly more grounded ideas on the endlessness or not so of the universe, however, relatively speaking. The Big Bounce is arguably one of the best-known models other than the Big Bang, popular because it proposes only certain small tweaks to the Big Bang, although those tweaks do have major implications. Big Bouncers suggest that, while the universe is expanding at an accelerated rate right now, that expansion will one day slow, and slow, and slow, until eventually it stops altogether and hits reverse. In what's otherwise at that point known as the Big Crunch scenario, the universe will retract and compact back in on itself. Galaxies will unavoidably draw closer and closer and closer toward one another. Matter in general will become denser and denser, all the way back until, once again, everything is held within an infinite singularity. Where that might have been the end of all things, however, the Big Bounce model argues that there's energy enough for a rebound, and that this massive event would result in another version of the universe emerging out of that recompacted singularity. The fundamental parts might be totally different. It might be a universe in which life is literally impossible, or one in which life is literally everywhere. But no matter the conditions, the cycle will begin anew. The Big Bang leads to accelerating expansion, leads to slowed expansion, end of growth, universal contraction, and a return to the start. Over and over again, an infinite number of times. In terms of neatness, it's perhaps one of the most satisfying models around, although there isn't any especially widespread support for the Big Bounce. Maybe it's just too neat to be true. Our fifth theory is another that could be described as neat as well, although it's also much more flexible. Ideas on space-time as a superfluid are both quite recent and fairly well entrenched in the history of physics, depending on how they're understood. In some ways, we can start with traditional, even classical ideas on the ether, a kind of unknown substance that scientists once believed the universe was bathed in, a mysterious medium through which waves of energy and light could travel. Those vague ideas have fallen by the wayside in recent times, but have also been replaced by other follow-on concepts. One is the continued debate over dark energy. What is it, where is it, and how closely it relates to our reality? But another is superfluid spacetime. First proposed in a big way in 2014 in a paper by the physicists Stefano Liberati and Luca Macchione. The notion is that spacetime could in fact be a fluid at the very, very smallest scale. And also that fluid might display zero viscosity and friction. It's perhaps a bizarre phenomenon to consider, that everything you are, see, know, and think is really kind of floating in a universe-sized vat of spacetime. But scientists believe that if it is true, then it could go some way to describing quantum gravity as an effect of space-time superfluidity. And of course, if we could land on a theory of quantum gravity, in whatever guise, then we could well finally have developed a true theory of everything. Heading into the second half of today's video, and have you ever wondered why everything seems so perfect around here? Okay, perhaps not in our daily lives, where war, disease, fear, and worry are basically ever present, but at the most fundamental levels of reality. Isn't it all very lucky that everything just works? Atoms are built as they are, molecules combine as they do, the laws of thermodynamics all run reasonably well, gravity, while ever-changing, does at least work as a concept. The speed of light, the rules of motion, they all combine to make our universe exactly what it is. If even a tiny amount of any of it were different, then really the entire thing could be totally changed. So why isn't it? This is known as the fine-tuning problem, and we've covered it in videos before. But one proposed solution is what's sometimes dubbed as the Goldilocks universe. That is, this is a universe that's just right for us and everything else that's in it. That's the true reality as to how and why things work. It sounds quite simple, but really it's not. Because how many attempts were there and are there still ongoing besides this universe we know? With such an extreme, eye-watering number of possibilities for all the variables at play, it's actually impossible to put a number on it. And so again, the idea suggests that there should really be infinite realities out there somewhere. It's an approach that can be further divided, though, into the weak and strong anthropic principle. Broadly, the weak anthropic principle argues for some kind of collective pool, what some might call a multiverse of universes, out of which ours emerged as one of many. In contrast, the strong anthropic principle in part suggests that life is a kind of predisposed element of the universe, that the universe must be observed, and so the observers, i.e. us and any other comparable life form, are built into it. If nothing else, that would certainly explain why you're watching this video. Theory number 7, and it's a must-know for anyone with even a passing habit for contemplating the nature of their existence, the simulation hypothesis. With roots that trace all the way back to the Enlightenment and René Descartes, the leading voice for today's generation is Professor Nick Bostrom, who first coined the term simulation hypothesis in a groundbreaking 2003 paper. In short, the underlying idea is that if an ancestor sim is ever possible, That is, if it is ever possible to build a world and populate it with genuine life, then the chances are almost certain that we're in one. Unless we blindly assume that we are the most intelligent life that there's ever been, and that we will therefore build the first ancestor sims at some point seemingly soon in our future, all of which is statistically very unlikely, then we have to conclude that some other higher civilization has beaten us to the punch. And not only that, but that they exist in a higher plane of reality, at least once removed from our level, meaning that we could never have beaten them anyway, because again, they made us. What's particularly weird from a this universe point of view, however, is that some advocates argue that reality being a sim can explain why so much of the cosmos is still so unknown to us. Every other planet that's not Earth is seemingly impossible to get to, or even to see in detail, because the sim runners don't want or need us there. They just like us to have some kind of curiosity about what might exist beyond our world. But those details aren't achievable for us because they aren't even properly rendered into the sim. There are emerging ideas, too, that the same could be said when we try to explore the quantum level, that subatomic particles break the laws of physics because it's there that we reach the limits of our sim's programming. And then, overshadowing all of that, there's the seeming possibility that if the universe is a sim, it could one day be switched off, or that it could be left to just glitch itself into shutdown. Or finally, that life's realization of its sim surroundings would be enough to break it irredeemably. So maybe this is one theory we shouldn't dwell on too long. It's perhaps only a short journey of the mind to our eighth model of the universe, however, the holographic universe. And yet, this one is actually quite fundamentally different to all of the others as well. The holographic principle, the basis for the holographic universe, proposes that everything we know is actually a 3D projection off of a 2D space. Rather than adding dimensions to explain reality, as so many other theories do, this one actually takes one away, arguing that any depth we might see around us is actually an elaborate illusion. In the everyday world, a true hologram is also a 3D image shown on a 2D surface thanks to some complicated tricks of the light. But scale that up to the universe as a whole, and you have a potential paradigm shift in terms of what we should consider ourselves to even be. In history, the idea has been closely tied to problems surrounding black holes and the information loss that seemingly happens whenever objects are consumed by them. Physicists, including Stephen Hawking, came to one conclusion in the 1970s and 80s, that any apparently lost information might actually be saved in 2D at the black hole's event horizon. Then, with ideas on the holographic universe, it's as though the same thing is happening, it's just that now the 2D plane, or disk of information, contains everything that's needed to formulate literally everything we know. From there, it's encoded into the reality that we can see and feel and touch. Your body, then, ultimately scales down to just one tiny bit of 2D information. Your brains and eyes, the screen or smartphone you're looking at right now, your town, country, and planet. Even every intangible idea that's ever been. At its base level, somewhere very far away from here, presumably suspended in something that isn't even space as we understand it, because space is a projection too, it rests as one tiny part of a 2D master sheet. But if that hasn't melted your mind, then perhaps our penultimate theory will. Although it's still in its relative infancy in terms of the debate surrounding it. The autodidactic, or self-learning universe model could well become a major game-changer in the field. It dates to a lengthy, multi-authored initial paper released in September 2021, although some ideas within it do stretch further back. For example, notions around natural selection for the universe were actually first floated in the late 1800s, although it's only really now that they're starting to develop into something more. At its heart, the autodidactic universe theory, which was formulated with the help of Microsoft, argues that the universe as we know it could actually be a learning machine. A computer, for want of a better word, but one that's so much more powerful than our lowly selves can even begin to imagine. It's the learning part that's most important here, however, because this isn't just simple evolution, the likes of which we see in most other models, including the Big Bang. Instead of the universe, it's the laws of physics themselves which the researchers claim could be ever-changing. In theory, this could mean that the very parameters of the early universe might have been vastly different to what we have now, which might also change dramatically again by some point in the distant future. Here, the rules of physics aren't constant, but are instead a movable feast. which means that we might never be able to fully understand them. And beyond the realization that the universe is self-learning, we'll actually never achieve a theory of everything. At a time when, on plain old planet Earth, the fears over self-learning and untamable AI are growing, how should we feel if the universe works in much the same way? Perhaps more so than with any other theory covered in this video. It leaves the humble human being seemingly very small indeed, and totally at the mercy of reality. But finally, and it doesn't exactly get a great deal more optimistic, because we're talking about what will happen to eventually end the universe. There are actually a number of quite high-profile scenarios in contention here, including the Big Rip and heat death. But there are some other, slightly more unconventional proposals too, including the end of time itself. Essentially, this last theory is wrapped up in the problems of infinity. Most notably, that if time is infinite, then almost all other physical theories ultimately fail. Naturally, the infinite nature of time doesn't allow for an end, or even really for a beginning. But most models need both. And most struggle to account for infinity, meaning that everything that can happen is also guaranteed to happen. There are arguments, then, to say that time itself must end at some point, although no one is even a little bit sure about how exactly that would work. In one variation on a similar theme, there's some talk of a potential barrier of time as a hypothesized physical mechanism to eventually draw the universe to a close. In 2010, for example, one study even calculated that we would reach that barrier, if it did exist, in 3.7 billion years' time, at which point the universe would stop. If true, that would mean that the universe is now about 3/4 of the way through its total lifetime and fast approaching old age. But then if it did stop, what comes next? Nothingness? Or is even nothingness something when you really think about it? If you take time itself to be a uniting factor even across the multiverse, in whichever way that multiverse might exist, then would it be as though nothing were ever here at all? Although, of course, there'd also be nothing left to observe, that nothing was left. Clearly, humankind is still very much at a stage where we have far more questions than answers. And regarding literal reality and the cosmos, there are some major fundamentals that perhaps we're nowhere even close to finalizing. But still, there are plenty of good ideas to debate, all of which are pushing towards that unknowable end goal. The Big Bang, black hole cosmology, the brain world, the Big Bounce, superfluid space-time, the Goldilocks universe, the simulation hypothesis, the holographic principle, an autodidactic universe, and the actual end of time itself.